Section 5.2 is all about perpendicular bisectors. So let's start this section with defining what a perpendicular bisector is. A perpendicular bisector is exactly as it sounds. A bisector is a point, line, or plane, or ray that cuts a segment into two congruent segments. So specifically, a perpendicular bisector is a line, ray, or segment that bisects another segment but also is perpendicular to it at the same time. So a perpendicular bisector is a segment, ray, line, or plane that is perpendicular to a segment at its midpoint, meaning that it is bisecting it. If a segment or a line or a ray or a plane hits another segment at its midpoint, that means it is bisecting it. So once again, a perpendicular bisector is a segment, ray, line, or plane that is perpendicular to a segment at its midpoint. So not only is it cutting it into two congruent segments, it is also perpendicular to that segment. Another vocab word is something called equidistant. A point is equidistant from two figures if the point is the same distance from each figure. I believe that equidistant is pretty self-explanatory. Equa means equal, distant, distance. So a point is equidistant from two figures if the point is the same distance from each figure. Points on the perpendicular bisector of a segment are equidistant from the segment's endpoints. Let me draw you a picture. So here we have a perpendicular bisector. This is the segment that's being bisected, and this is the segment that is the perpendicular bisector. You can see that because this would be its midpoint, since this segment is congruent to this segment, and it's the perpendicular bisector because it is intersecting that segment to form a right angle. So what this last statement said was that points on this perpendicular bisector are equidistant from the segment's endpoints. So that means that any point on this perpendicular bisector would be equidistant to the segment's endpoints. So if I had a point right here on this perpendicular bisector, that point is equidistant to the endpoints of the segment that is being bisected. So those two red lines would be congruent to each other. And that is true for any point along this perpendicular bisector. If I had a point right here, the segment connecting to this endpoint and the segment connecting to this point, they would also be congruent. This leads us into the next theorem that we'll see on the next slide. And here's that theorem, 5.2, perpendicular bisector theorem. In a plane, which remember is just a flat surface, if a point is on the perpendicular bisector of a segment, then it is equidistant from the endpoints of the segment. So if you're looking at the diagram, this would be the perpendicular bisector of segment AB because it is intersecting segment AB at its midpoint, cutting it into two congruent segments, and it is also perpendicular to the segment at that point. So therefore, any point on this line is equidistant to the segment's endpoints that it is bisecting. So here we have point C. It would be equidistant from here to here and from here to here to the segment's endpoints. So that would mean that this segment is congruent to this segment. And that would also be true for any other point that is on the line of that perpendicular bisector. Every single point on this line is equidistant to the segment's endpoints. Next, we have the converse of the perpendicular bisector theorem, which is theorem 5.3. It states in a plane, so again, another flat surface, if a point is equidistant from the endpoints of a segment, then it is on the perpendicular bisector of the segment. So you can see here we have segment AB, and we have point D, which is not on it. Point D is equidistant to the segment's endpoints. Therefore, we can conclude that point D must be on the perpendicular bisector of segment AB. So here's an example. Number one, in the diagram, line RS, which is this one right here, is the perpendicular bisector of segment PQ, which is this right here. And they want us to find the length of PR. So we need this length right here. In order to find PR, we'd have to figure out what X is first. Let's first mark on our diagram based on the information that we're given. So we are told that line RS is the perpendicular bisector of PQ. So that means that this segment must be congruent to this segment, and this line is intersecting the segment to form a right angle. According to the perpendicular bisector theorem, we know that any point on this line, which is the perpendicular bisector, is equidistant to the segment's endpoints. So therefore, R is equidistant to P and to Q. So that means that PR is congruent to QR. So that means I can set up the equation and set 8x minus 9 equal to 6x. So again, my goal is to solve for x. So my first step would be to subtract 8x. So I have negative 9 is equal to negative 2x. Divide both sides by negative 2. And so I end up with x equals 9 over 2, which we can think of just as 4.5. So remember, my ultimate goal is to find the length of PR, not just to find what x is equal to. So to find PR, I'm going to plug it back into here. So PR is equal to 8x minus 9, and now I'm going to substitute 4.5 in for x. So it'd be 8 times 4.5 minus 9. And I end up with 27. So PR is 27. If PR is 27, so is QR. So once you know one of the lengths, you know the other length. And here's an example that uses the converse of the perpendicular bisector theorem. It says in the diagram, line JM is the perpendicular bisector of segment HK. So let's mark our diagram to show that. So if JM, which is this line right here, is the perpendicular bisector of HK, that would mean that this segment is congruent to this segment, and we already see that it is perpendicular right there. So point J is on the perpendicular bisector. So we know that from J to H would be the same from J to K. So we also know that this segment is congruent to this segment. So in the first part it says which lengths in the diagram are equal. So we already know that HM is equal to KM. So we already knew that these two segments were equal. And we also know that KJ is equal to HJ, these two segments, since J was on the perpendicular bisector of the segment HK. And we're also just told in our given information that this segment is congruent to this segment since they're both equal to 12.5. So LH is equal to LK. Our next question is point L on line JM? So since we know that point L is equidistant to H and to K, that means that L must lie on the perpendicular bisector of segment HK. So since JM is the perpendicular bisector of HK and L is equidistant to the segment's endpoints, then according to the converse of the perpendicular bisector theorem, we can say yes, point L is on line JM. We'll end this section with a bit more vocabulary. When three or more lines, rays, or segments intersect in the same point, they are called concurrent. So here's a picture of three segments that are all intersecting in the same point. So those three segments would be called concurrent. The point they intersect at is called the point of concurrency. So this point right here that all three segments are sharing is called the point of concurrency. And that brings us to the last theorem of this section, the concurrency of perpendicular bisectors of a triangle. It states the perpendicular bisectors of a triangle intersect at a point that is equidistant from the vertices of the triangle. I really like this diagram because they color-coded it for you. It says that if PD, PE, and PF, those are the segments in blue, so PE, PD, and PF, are the perpendicular bisectors. So if PE is the perpendicular bisector of BC, that means that E is the midpoint of segment BC. So I can mark on the diagram that BE must be congruent to CE and a right angle was formed. If PD is the perpendicular bisector of segment BA, that means D is a midpoint, and we know that BD would be congruent to AD, and there'd be a right angle formed right here. And finally, if PF is the perpendicular bisector of AC, that means that AF is congruent to CF, and a right angle is formed. So if we have those blue perpendicular bisectors, then PA is equal to PB, which is equal to PC. So all of the red segments are congruent. So where the perpendicular bisectors intersect, that point of concurrency, from that point, it is equidistant to the vertices of the triangle. So that means that this segment is congruent to this segment, which is congruent to this segment. That point where the three perpendicular bisectors intersect each other is called something specific. So the point of concurrency of the three perpendicular bisectors of a triangle is called the circumcenter. So once again, the point of concurrency of the three perpendicular bisectors of a triangle is called the circumcenter. We can think of that circumcenter P, since it is equidistant to the vertices of the triangle, we can think of that point as the radius of a circle that is drawn around the triangle, because this would become like radii of the circle. So I can draw a circle around it. That circle that is drawn around the triangle is said to be circumscribed about the triangle. So I give you three different examples here. The first one is an acute triangle in the first picture. So what we find here is point P, which is the circumcenter, which again is the point of concurrency of the three perpendicular bisectors. So we know that the circumcenter is equidistant to the vertices of the triangle. So drawing a circle around those vertices, making that distance the radii of the circle, we have this circle that is circumscribed around the circle. Next, we have a right triangle. Notice that in a right triangle, the circumcenter actually ends up on the hypotenuse of the right triangle. That point is equidistant to the vertices of the triangle. So when you draw the circle around it, you have your circumscribed circle around the triangle. Next, we have an obtuse triangle. So we have an obtuse angle right here. Notice that when we find the circumcenter, the point of concurrency of the perpendicular bisectors, it is actually outside of the triangle. So we know that from that point to all three vertices of the triangle, we have an equidistant distance. So we connect all three of those points and we have our circumscribed circle around the triangle. That's it for this section. I realize that that's a lot of information, so clearly we will go over this a lot in class and solidify all of this before we move on. As always, write stuff down if you don't understand them, and we'll cover that in class before we move on, and we'll see you then.